Okay, today we're going to be talking about lecture 34, which was on entropy. Before we get into entropy, we're going to talk about spontaneous processes. A spontaneous process is a process that will continue happening without ongoing intervention. So, for example, a punctured tire. Air will continue to move out of the tire once it's punctured, and it will not run back into the tire. The same concept applies to iron rusting. Iron will continue to rust once it starts, and it will not become shiny again on its own. In our language, spontaneous means that it just happens. But in chemistry, a spontaneous process does not always mean that a process will just happen. Some spontaneous reactions still need an initial push, but once a spontaneous reaction has started, it will keep going without further stimulation. So back to the tire example, that initial push was that first poke into the tire, exposing a hole. After that initial push, the air just continues to run out. We don't have to keep poking holes for air to continue to move out of the tire. Temperature also affects spontaneity. Some processes are only spontaneous at certain temperatures. For example, ice will melt and keep melting, which makes it spontaneous. But ice will only melt at temperatures above its normal freezing point. So if you take an ice cube and you stick it in the freezer, which has a temperature below its freezing point, that ice cube will not spontaneously start to melt and continue melting. But if you take that ice cube out of the freezer and set it on the counter, now the ice is in an environment that has a temperature higher than its normal freezing point. And so now the ice will spontaneously begin to melt and continue melting without applying any more heat to it. This same idea applies to cake batter. When you mix all of the ingredients together and you create cake batter, that cake batter does not just start turning into a cake. But if the cake batter is placed in an environment of the correct temperature, such as an oven, then the cake batter will start turning into and keep turning into a cake. So how does this apply to chemistry on a molecular level? A spontaneous reaction is a reaction in which the particles and the particles in the products of a reaction are more spread out and or have more freedom of motion than the particles in the reactants of the reaction. So let's look at this example of solid water going through a reaction to become water vapor. We know that solid water's particles are tightly packed together and do not have much freedom of motion. And we know that water vapor's particles have a lot of freedom of motion because they're very spread out. So if we have a reaction going from solid water to water vapor, that means that we are increasing our freedom of motion for the particles, which means that that reaction is spontaneous. If you were to have a reaction in which you went from a gas to a solid, that would mean that it was not a spontaneous reaction because you're going from something that has a lot of freedom of motion to something that does not have very much freedom of motion. So how does this all apply to entropy? Entropy, which is depicted by the letter S, is a measure of how dispersed the energy in a system is at a specific temperature. In other words, entropy is a measure of chaos. Let's go back to the solid water to water vapor example. A gas's particles have more freedom of movement than a solid's particles. This means the energy in the gas can disperse more easily than the energy in the solid. So that water vapor can disperse its energy much easier than the solid water. This means that gases have a higher entropy than solids. In other words, gases are more chaotic than solids, because in a gas, the energy is free to move about, to disperse, so it is more chaotic, has a higher entropy. But a solid has its particles tightly packed together, which means that we don't have a lot of dispersion of that energy, and we have a low chaos level or entropy. The second law of thermodynamics applies to entropy. In the second law of thermodynamics, we see here that the delta or change in entropy of the universe is always greater than 0. In other words, every reaction in the universe will increase the entropy or chaos of the universe. So if entropy is the measure of an energy dispersion, then we must look at how energy can be dispersed. And to do that, we're going to talk about something called microstates. Microstates are possible arrangements of energy dispersion. In this picture, we see an example of microstates. This first column is the first microstate, or the first possible arrangement of energy dispersion for these particles. We see that we have 2 spheres connected by a tube, and we have 4 different particles within that sphere. In this first microstate, or this first possible arrangement, we see that we have all of our particles in the left sphere and no particles in the right sphere, meaning that our energy is dispersed so that all of our energy is on the left side and none of our energy is on the right. We also see that there is only one way to get this specific energy dispersion, or microstate. Going on to the second column, or microstate, we see that we have 3 particles in our left sphere and 1 particle in our right sphere. This means that we have more energy on the left and less energy on the right. We also see that we have 4 possible ways to get this specific arrangement of energy dispersion, or this specific microstate. Going on to the third column, we see our equal dispersion of energy in this microstate. We have 2 particles on the left, 2 particles on the right. We also see that there are 6 possible ways to get this energy dispersion. And then it goes on from there. So the most probable microstate is the one that has an equal dispersion of energy, as we see in this example, where we have 2 particles on the left, 2 particles on the right, meaning we have an equal dispersion of energy. We have 6 possible ways to get that dispersion, whereas in the other microstates, we only have 4 and 1 possible way to get those. So this applies to all reactions, that the most probable microstate is the one that has an equal dispersion of energy. You can calculate the entropy of a certain microstate through Boltzmann's equation. Boltzmann's equation is here on the left. We see that S, or entropy, equals Kb, which is Boltzmann's constant here. Boltzmann's constant equals 1.38 times 10 to the negative 23rd joules per Kelvin. And Boltzmann's constant represents the probability of being in a certain microstate. So we have entropy equals Boltzmann's constant times the Ln, which is the log base E, it's a button on your calculator, of W. And in this case, W stands for the number of possible microstates. So if we were to use this equation for this example, we would have 1, 2, 3, 4, 5 possible microstates. So we would be doing the entropy of that reaction would be Boltzmann's constant times the ln of 5. And this value will be given to us whenever we're using Boltzmann's equation. So, what influences entropy? First, we're going to talk about mass. If we have a higher mass, that means we have more atoms. When we have more atoms, there's more possible dispersion of entropy, which gives us a higher, more dispersion of energy, which gives us a higher entropy. Let's look at this example of glucose and water. In this water molecule, we see that we have 3 atoms, which means that our energy can be dispersed between 3 atoms. Whereas in this glucose molecule, we have much more than 3 atoms, meaning that our energy can be dispersed in many more ways than just 3. So our glucose molecule is going to have a higher entropy than our water molecule. Next is molecular shape. The more spread out or linear the shape of a molecule, the easier it is for energy to be dispersed throughout that molecule, which helps us have a higher entropy. We can see this here looking at this linear molecule and this branched molecule. In a linear molecule, our atoms are bonded to less atoms, meaning that these individual atoms can rotate and translate more easily, which disperses energy more efficiently. Whereas in this branched molecule, we have our atoms bonded to more atoms, which means that we will have a harder time dispersing our energy, which gives us a lower entropy. Rigidity is very similar to molecular shape. The more linear a molecule is, the less rigid it is. So if we look at this linear molecule, we know that that line is going to very easily move about and change its shape, and that will help us disperse energy. Whereas in this branched molecule, it's going to be hard for that molecule to move about, which will make it harder to disperse energy, which will result in a lower entropy. Next is our number of independent particles. The more particles you have, the more dispersion you have, the higher entropy you have. So this would apply to something like we have a reaction that starts with 1 molecule and it produces 2 molecules, meaning that our reactants, we only have 1 molecule, so there's only 1 space for that energy to disperse within. But in our products, we have 2 molecules. We have more independent particles, so we have more space for our energy to disperse. Next is volume. If we have a higher volume, we have more space for energy dispersion, which means that we will have a higher entropy. And lastly is temperature. If we have a higher temperature, that means we have an increased kinetic energy of our particles, which means that our particles are moving about, bouncing into each other, rotating, translating, which all results in more energy dispersion, which results in a higher entropy. So how do we calculate entropy? First, we can look at the equation that the delta, or change in entropy of a reaction, is equal to the final entropy minus the initial entropy of the reaction. We also know that entropy is a state function, which means that we can use Hess's law to calculate our change in entropy of a reaction. That means that we're going to be using this equation here. Our change in entropy of a reaction is equal to the sigma, or the sum, of the entropy of the products times the moles of the products minus the sum of the entropy of the reactants times the moles of the reactants. When using this equation, our S values are given to us, or they're found in the appendix of the textbook. Something that's important to remember, because this equation is basically the same equation as finding the delta H of a reaction. Remember that unlike the delta H of formation values, where pure elements are equal to 0, entropy values for pure elements are actual values, not 0. So let's practice this. So we are going to use the values in the table to calculate the delta H of a reaction and the delta S of a reaction. I wanted to include the delta H of the reaction in this example so that we could see again that the delta H of formation of a pure element here, copper, is 0, but the entropy value of pure element copper is 33.2. So again, we see that it is not 0 for the delta S. So we are going to use this reaction where we have copper to oxide, turn it into copper monoxide and elemental copper. We're going to use this equation for both the delta H and the delta S. For our delta S, we're going to do our products minus our reactants. And we only have 1 mole of each of these things, so we're not going to have to multiply by this n. We're not going to have to do that. So we take our delta H of formation value of copper monoxide here, negative 156.1 here, plus our delta H of formation value of copper here, which is 0, minus our reactants, which is our copper 2 oxide, and we're going to have that be negative 170.7, so minus the 170.7. And that gives us a value of 14.6 kilojoules. Now we do the same thing for the delta S of the reaction. We're going to find our value for our copper monoxide. That's going to be 42.6 here, plus our value of copper, 33.2, minus our value of our copper 2 oxide. And that is going to be 92.4. That gives us a value of negative 16.6. What do these values mean? For our delta H, we have a value of positive 14.6 kilojoules. That means that this reaction absorbs 14.6 kilojoules of energy. For our delta S, we have a negative 16.6 joules, which means that in this reaction, we release 16.6 joules of entropy, or we become 16.6 joules more orderly, less chaotic. All right, and lastly, we're going to talk about the third law of thermodynamics. The third law of thermodynamics states that a perfect crystal at absolute 0 Kelvin has an entropy of 0. This can be shown in the equation. S, or entropy, equals Boltzmann's constant times the ln of 1, which equals 0. So why do we have this 1 here for this equation? As we can see in this depiction of a perfect crystal, our particles are perfectly aligned and packed very tightly together. There's not much freedom of motion. There's not very much room for energy dispersion. And on top of that, we are at absolute 0 Kelvin, which means we're going to have a very, very small amount of particle kinetic energy, particle movement. And so with the packed tight particles in the crystalline structure at the absolute zero temperature, we get that there is only one possible way that the energy of this crystal can be dispersed, that there is only one possible microstate. So remember that in this equation, this is our W value, which is the number of possible microstates. And in this instance, where we have a perfect crystal at absolute 0 Kelvin, we have only one possible microstate. And that gives us an entropy or chaos level of 0.